Today we're going to be talking about integrated rate laws. I want you to be sure to pay attention to the disclaimer I'm about to talk about. This video is really a quick covering of the topic that we're going to actually explore further and reinforce in a class activity. So it's really important that you do watch this video, pay attention to the video, and if you still find it confusing, you need to go to the Westlake High School AP Chemistry YouTube channel and watch the full lecture. You can find that lecture in the Kinetics playlist, and the video is called Integrated Rate Laws. The graphing of integrated rate laws is our third and final way to find a rate law. The rate law that you're used to seeing is what we call a differential rate law because it describes the change in concentration of reactants per a change in time. Using calculus, and don't worry, you don't need to know calculus to do what we're going to do, the rate law can be integrated, and what that does, it links concentration of reactants and products with time directly. That allows us to graph the relationship, and from that graph we can determine the order, and we can also determine the numerical value of K. Today we are going to focus on the integrated rate law for zero order, first order, and second order. Let's begin with the zero order reaction. So if we have reactant A going to products and we wrote the rate law for reactant A and it happened to be zero order, we know the rate law would look like this, where rate is equal to K times the concentration of A raised to the zero order. Now, if we were to integrate this rate law from time 0 to time t, we would get the following integrated rate law, where the concentration of A minus the concentration of A naught equals negative kT. A is the concentration at time t, A naught is the original concentration, K is your rate constant, and T is the amount of time the reaction ran. We can utilize these rate laws to solve for any one of the variables given all the other information, and you're going to experience that in the activity that you'll be doing in class. However, one of the most important things that we do with this integrated rate law is linearize it for the purpose of graphing. So to linearize this, all I need to do is take this negative A naught and add it to both sides, ultimately swinging it around to the other side of the equation, and I get the following equation. If you look closely, you can see how that resembles the linear function, where y is the concentration of A and B is your y-intercept, which is your initial concentration, and your slope is equal to negative K. So when you do graph this relationship, you will get the following graph. Again, when you want to graph a zero-order relationship, you need to put time on the x-axis and concentration on the y. It's very important to pay attention to the slope of this line. The slope is negative. It's going to be a factor that you're going to use in identifying what order of a reaction you may come across. Also, the slope is equal to negative K, so whenever we need the numerical value of K, after we graph, we're going to take the absolute value of the slope, and we now know that value. Now let's take a look at a first order reaction. You can see here again, if our reactant is A and it's first order, the rate law is equal to rate is equal to K times A raised to the first order, the first power. If we were to integrate this rate law from time 0 to time t, we would get the following rate law. Natural log of A minus natural log of A naught equals negative kT. That actually comes from the calculus. Good news, this is on your AP sheet. You do not need to memorize it. However, it is not labeled as a first order. It just has the equation by itself. So you're going to need to recognize that this is the natural log one is the one that you correlate with the first order. Again, like we did last time, we're going to linearize this puppy. So we're going to take that natural log of A, swing it around to the other side. And when we do that, we get this equation that again has linear characteristics. So if we wanted to prove an order was first order, we would graph it this second way, which is natural log of concentration versus time. Remember, zero order was just concentration versus time. This one is natural log of concentration versus time. Our slope is still negative, and if we want to find the value of K, we would take the absolute value of said slope. And finally, we're going to take a look at a second order reaction. Again, A is our reactant, and if it's a second order relationship, we know that the rate law would be rate is equal to K times the concentration of A raised to the second power. The integrated rate law for this, from time 0 to time t, is 1 over A, or 1 divided by A, minus 1 divided by A naught is equal to positive KT. That's a difference, it's a subtle difference, but it's super important to pay attention to. So to linearize this one, like before, we're going to take this 1 over A naught and bring it over to the right side. Why we choose that one is because that's a constant. Our initial concentration stays constant, so that will, of course, represent the y-intercept in our relationship, as you can see here. This time, we're going to graph it, and again, we're going to get something that's linear. That's why we linearize it, but our axes are this time 1 over A, or the reciprocal of A, on the y-axis and time on the x. And this time your slope is positive. Super important to pay attention to that for means of identification. The AP has been known to give you a graph and say, hey, what's the order? And sometimes you know it's second just because the slope is positive. So pay attention to that, make note of it, and let's go ahead and compare all three scenarios. Oh, one thing I actually failed to mention was that this is on the AP equation sheet along with the first order integrated rate law. They are listed in order. First is the first and then is this one. They are not labeled, but at least you don't have to memorize it, which is good news. You just have to recognize it. Now let's go ahead and compare all three scenarios together in one big chart. So here is a summary of all the information you need to know. You're going to be provided with a copy of this when we're doing the activity, so it'll be useful in your studying. What I have first are highlighted the things you do need to memorize. So zero order, you do need to memorize this equation, but if you notice, it's identical to these, other than the fact there's no natural log or no reciprocal. It's always A minus A naught, so this should not be a difficult one to memorize. You also need to know how to graph all three relationships and the differences in the graph, specifically this positive slope situation. We're going to go over how to graph in the calculator. I have a very quick and, as I always call it, sexy way to make this graphing happen within a couple minutes, so we'll go ahead and learn that in class. A memorization tip for this, graphing should be clear to you now, as in concentration versus time, natural log of concentration versus time, reciprocal in concentration versus time. C, concentration, L, natural log, R, reciprocal. This should help you out a lot in your memorization tasks and learning how to analyze these graphs. So, what is the business with this half-life situation? Let's talk about that because there's one important thing I need to mention to you. So, what is a half-life? A half-life is the amount of time it takes for half of a substance to react or to disappear when a reaction is occurring. Here are the half-life equations for a zero, first, and second order reaction. Where did they come from? Well, this is the assumption that was made. We know that when one half-life passes, the original amount is cut in half. So that would be equal to the concentration at time t, or at one half-life. So what was done to derive these was the substitution of A naught over 2 anywhere we had A in the equation. I don't want you to get overwhelmed by that. I'm just wanting to show you that rearrangement and point out a very important part that you need to understand. So if you take a look at the zero order equation, A naught over 2 was plugged in right here where A was, rearranged, and we got down to this equation right here. You do not need to memorize that equation. What's important is when we get to the first order, and this is the part that you really need to pay attention to, something you need to notice. If I take A naught over 2 and plug it in and do all the math and rearrange, I get this equation. This might look familiar to you. This is the half-life equation of nuclear reactions. All nuclear reactions are first order. What's important to notice here is that in zero order, for instance, initial concentration is present in the half-life, meaning As the initial concentration of your reactant changes, your half-life changes. But whoa, first order, no initial concentration in here. What that means is that in a first order reaction, half-life is constant. Just like with any nuclear isotope that we talk about, we know uranium has a set half-life, right? Doesn't matter how much uranium you have, you're going to have the same half-life. Same thing with all your other radioactive isotopes. That's what's specifically important about first order. And when we look at the second order derivation, again, plugging in A naught over 2 for A, rearranging it, we get another equation where the initial concentration is present, and again, that will affect the half-life. That will change the half-life depending upon what that start concentration is. There will be many instances on the AP where you might have to analyze data, and looking at the data you see, oh, every 10 seconds the concentration splits in half. And that means the half-life is constant, and that means it's got to be a first order. So it's really super important for you to connect the fact that first order is independent of initial concentration when it comes to half-life. And it's so important that they actually give you the first order half-life equation on the AP exam. You do not have the others. I don't think you need to memorize them because I think you had to derive them. You could. So just focus on understanding the difference in the first order half-life and potentially being able to use that equation to solve either for half-life or for K. Okay, well that's it. That's my synopsis on integrated rate laws. Next class, we're actually going to be practicing using and graphing and getting acquainted with these in our activity. So if you have somewhat of an understanding, don't worry, we'll deepen that understanding in class. Again, if you are struggling and you are like, oh my God, I have no idea what this lady was talking about, please go watch the video on the YouTube channel in the kinetics playlist. That's it. Have a great day.